This is the lecture video for section 2.7 in the textbook on functions of random variables. It's a shorter section, and we're really just going to wrap up our discussion of probability and probability density functions. We'll also introduce the notion of variance, which is related to standard deviation. Our goals in this lecture are to, first of all, understand what it means to have a function of a random variable, and then learn how to compute expected values of such new random variables. Related to this, but slightly separately, as it'll appear in this lecture, we'll learn how to compute the average value of a function. And finally, we'll learn about the variance of a random variable, how to compute it, and then from it, how to extract the standard deviation. So first of all, what is a function of a random variable? Let's suppose that we have, in the first place, a discrete random variable, capital X, and we can write down some probability distribution function, f of x, which so far we haven't really written down distribution functions for discrete random variables, but you can think of this f function as returning a value equal to the probability of that particular little x value occurring. For example, if we have some four-sided die with these four values, 0, 2, 3, and -2 painted on the sides, then the probability of rolling those four values are given by the probability function f sub x for that variable. Now that's sort of a contrived situation, but we can think of this as some finite or discrete random variable situation, and the function f describes the probabilities of each of the outcomes. On the other hand, let's suppose that for some reason we want to compute the probability not of x occurring, but of x squared occurring. So we really want to look at the values of this random variable and then square them. We'll call that a new random variable, capital Y. And we can think of Y as a function of capital X, where the function in this case is G squares the random variable. The probability distribution function, we'll call this now f sub Y of a new variable Y, describes the probabilities of each outcomes occurring where the outcome is of this new random variable, capital Y. So I think at first glance, it's worth pausing here and reading this again and comparing the two descriptions of these probability density functions for yourself to really understand what's going on. Here, the f sub x values are a probability that the x random variable takes on the value 0. So there's, for example, a 30% chance that the capital X variable takes on a value of 3. On the other hand, the f sub y function is describing the possible values of the x squared variable, which we also call capital Y. So if the new random variable x squared is to take on the value 4, well, apparently there's a 60% chance of this happening. Let's see where that comes from. To get y equals 4, we should have started with something whose square is a 4 that is either coming from x equals 2 or x equals -2. And together, the probabilities add up to 0.6 or 60%. And that's why we have a 0.6 over here. So these are relatively easy to compute once you get your head around what's actually going on with taking a function of a random variable. But we might want to do this in a continuous situation. Or we might want to do this where the function g isn't really something we can write a formula for, like x squared on the previous slide. For example, let's let x be a discrete random variable again, so it has finite or countably many outcomes. And the outputs of this random variable, the possible events that can happen, are integers from 1 to 100. They will be uniformly distributed. So they each have a 1 in 100 chance of occurring. That's what a discrete uniform distribution is. And from x, we're going to form a new random variable called capital N, which is a function of the random variable x. And if we look at a value that x can take on, the corresponding value of n will be the number of digits of that number from 1 to 100 that appeared in our variable x. You should think of this, and we really should think of a lot of probability theory as taking a sample from some population or some data that we don't have full information about. In this case, we do have full information, but we'd have to count it all. And if the data we extract with x is the number itself, then the data that capital N extracts is the number of digits of what we extracted using x. You can really think of capital X and capital N as two different processes where n first assesses what happened with x and then produces new information, namely the number of digits. Let's look at the probability distribution, or the density function for f for capital N. If the number of digits of the number that we select from our data set is 1, how many numbers have it? How many numbers from 1 to 100 have 1 digit? Well, there are 9 of them. The numbers 1 through 9. So there's a 9 out of 100 probability of choosing something with 1 digit. Similarly, there are 90 out of those 100 numbers that have 2 digits, and a single one with 3 digits. That's just 100 at the end of the list. For any other possible number of digits, there's a 0% probability of selecting a number with that number of digits. So this is just how in a continuous situation outside of a certain interval, here's outside of these 3 particular values, we don't have any probabilities. So that's the distribution function. And there's some things that we'd like to do with distribution functions. Namely, we can use these to add up more complicated probabilities. What is the probability of selecting a number with at least 2 digits? Well, in that case, we can add together the probabilities of getting 2 or 3 digits, and that's done with this probability function. Or we can double check that this adds up to 1 and actually is a probability function. We can also compute expected values from this. So we can compute expected values directly from the distribution function, and we have a formula for this that we learned in a previous lecture. For example, for the previous situation where capital N is the number of digits of our random sampling from 1 to 100, we can compute its expected value by finding each potential output value. The number of digits can be 1, 2, or 3, and then multiplying each of them or weighting each of them by their corresponding probability. If you look at the density function on the previous slide, the probability for 1 was 9 out of 100, and here are the other probabilities. If you multiply and then add these up, you'll get 1.92 as the expected value, or the expected number of digits of a random sampling from 1 to 100. So, take this back to dinner with your family next time and say, how many digits on average should you expect from a number from 1 to 100? And they'll say, what the hell are you talking about? And you can say, well, the answer is 1.92 if you're curious. There's another way to handle this, and there's actually a couple more ways that we can compute things. So because each of the outcomes of capital N actually rely on an outcome of capital X, that's what it means for N to be a function of X, the original random variable, just selecting the number, we can assign a probability to each of the states or outcomes in the variable capital X and add those up separately. So what's really going on in this formula is if we take each of the possible values, and here we want to convert them to their number of digits to get an expected value for N, but the number 1, 2, 3, all the way up to 9 have 1 digit. That's why you see a 1 in parentheses here, and they each have a 1 in 100 probability of occurring. The next 90 numbers on the list have 2 digits, so from 10 all the way up to 99, they each get a 1 out of 100 probability since it's a uniform discrete distribution. And finally, 100 has 3 digits, so it's going to show up last with also a probability of 1/100th. If you add these up, you'll get the same answer, 1.92. And the reason is that this is really just breaking out each of the probabilities on the previous slide into a sum over all possible X values that determine those N values. We should be a little more efficient about this though. So if Y is a function of X, we can write it as Y equals G bracket X to mean a function of capital X. Then we can compute the expected value of the new variable Y, either using the distribution for X or the distribution for Y. And those were the previous 2 slides, the 2 computations we showed that both gave 1.92. So the expected value for Y is either a sum over potential outcomes for the Y variable, yi times the probability that yi occurs, or alternatively, we can compute it as a sum over all outcomes for the X variable. That was the longer computation a moment ago of, well, not the outcome xi, but the y outcome corresponding to xi, or in other words, g of xi, times the probability that that outcome occurs for the X variable. So here you'll see f of x xi. We can equate these formulas We can actually show that these are equivalent formulas by making the following substitution, which if you want to pause the video and try to work this out, it just explains how these two are the same. It requires just unpacking the notation on the right side here, but in words, it's exactly what we just said out loud. Both formulas give us the same answer, and you might say, well, adding up over 100 numbers versus adding up over 3 different possible outcomes is much less efficient. The key here, though, is that in order to add up this smaller data set, the outcomes for y is a smaller list to add over, we actually have to know the distribution function for y. And in the previous example, this was possible, but in general, it's difficult to find distribution functions for new random variables. So the second option, which is the longer one, gives you the same answer and might be the only option that you have. Let's see what happens for continuous random variables. And this is really where things will get tricky, finding a new distribution function. But let's suppose that we have a continuous random variable x and form a new continuous random variable capital Y that's some function of x. And in this case, we really hope we have a formula g of little x that describes this. In order to compute probabilities and compute expected value of capital Y, we first would need to find a new density function f sub capital Y that, what does it mean to be a density function? It has to integrate over intervals a, b to give the probability that new variable y lands in that interval. It also has to have the non-negative property and integrate to 1 over the whole real line. But to compute the expected value, we'd have to integrate y times that function. And first of all, it might be difficult or impossible to write down a new density function for y. And on top of that, it also might be a difficult integral computation. We might have to approximate or something. So how do we get around this? Well, let's use the other formula where we add up over the states in capital X. And if we convert this into a continuous formula, explicitly, if we take a limit of the discrete situation, we'll get an integral. And the following is a theorem that we won't prove, but the theorem says that we can instead compute the expected value of y using an integral with respect to the variable x of g of x times fx of x dx. So it's an integral over all possible values that the original variable capital X can take on. So it's some entire real axis. But in this case, instead of weighting y values by their probabilities, we're weighting output values, these are secretly y values, by their probability of occurring with respect to the x distribution. So to practice this, let's look at a familiar continuous random variable x with density function given as shown here. We've already dealt with this function before, and I believe we computed the expected value. But what we want to do here is compute the expected value of a new random variable, capital Y, which is given by e to the capital X. So what that means is the outcomes of the new variable are the e raised to the outcomes of the original variable. Let's work this one out together using that theorem that we just wrote down. Keeping in mind that it might be difficult or impossible to come up with a separate f sub capital Y function for this new variable. And by the way, I'm calling this new variable capital Y in the below. So here's the formula and the theorem we just learned. Let's use this to compute the expected value of e raised to the capital X. So the expected value there is going to be the integral from -infinity to infinity of g of x, which is the function that tells us how to get the new random variable. In this case, this will just be e to the x. Remember, this is supposed to be g of x times the original distribution. In this case, I'm going to leave it as f sub x of x dx, because over the whole real number line, this takes on different values. However, we know that outside of the interval 0 to 3, the function takes on the value 0, so it's enough to integrate from 0 to 3 of e to the x times that distribution. I'm going to rewrite it as 1/9 x squared times e to the x dx. All right, we're done with the stuff above. Now we're just computing this integral to find the expected value. So here we go. this is of the form algebraic times exponential, and it's not one we can do with a substitution. So this looks like a job for integration by parts. This is another good opportunity to pause the video and practice your integration by parts if that's something you want some more practice with. I'm going to keep going and write down our u and dv choices. So u here using I late is going to be 1/9 x squared, which means that du is 2/9, 2/9 x dx. dv is everything else that's there. It's just e to the x dx, which means that v was e to the x. I'm going to compute this as an indefinite integral and then go back and make the substitutions with 0 and 3 later. So the integral of 1/9 x squared e to the x is given by u times v, 1/9 x squared e to the x, minus the integral of v times du. I'm going to rewrite things as 2/9 x e to the x dx. This is another integral that we need to solve with integration by parts. So separately for this thing, I'm going to make a new choice of u bar. That'll be the algebraic part again, 2/9 x. And du bar then is 2/9 dx. Look how the complexity of the u part of the function went down. That means that dv bar is everything left over. That's still e to the x dx, and then v bar was e to the x. I guess you could have reused the variable v here since it's the same, but I'll just be careful about it. So this whole expression then becomes, well, we have the same leading term. And then I'm subtracting this integral, which is u bar times v bar, 2/9 x e to the x, minus the integral of v bar times du bar. It's going to be 2/9 e to the x dx. And let's solve this and get our antiderivative that we need. Be careful with distributing minus signs here. I see there's a minus minus, so I'll make it a plus. If I integrate this, this is just an integral of an exponential by itself. That's 2/9 e to the x dx. I need a plus c if I'm being really, really careful here. But now let's go back and compute the definite integral that we wanted, which was 1/9 x squared e to the x dx. We have now found an antiderivative of this function in the integral. So that's what we'll use to do the fundamental theorem of calculus. So just copying this down. Plus 2/9 e to the x. Oops, there's a dx that snuck in there somehow. Sorry about that. And we're evaluating this from 0 to 3. So at this point, we could use a calculator. Oh, look here. You can see the answer down below because I wanted to give you a decimal answer and not waste any time in the video. But let me carefully write down a couple more steps to get down to that answer. If I plug in x equals 3, we'll get 1/9 times 9. I'm just going to cancel those out, and then we'll have e to the 3 minus, if I plug in 3 here, I'll get 2/9 times 3 is 2/3 e to the 3 plus 2/9 e to the 3. And almost everything is 0. We get a 0, a 0. We also get a 2/9 e to the 0, which is 1. So we'll just get a 2/9. That's everything plugged in. If you carefully get common denominators here, you will get 5/9 times e cubed. And then we're also left with the minus 2/9. So this is the expected value of the new variable e to the capital X. And just for a gut check, the expected value of this variable is 10.94, which at first glance is alarming since the original interval of outcomes was 0 to 3. But remember that our new variable is e raised to those values. So as long as this 10.94 figure lies somewhere on the interval, not from 0 to 3, but from e to the 0, which is 1, to e to the 3, then we're safe, then this is valid. And you can check that e to the 3 is something like 20 point, I forget, it's something over 20. So we're in good shape for this. Let's keep moving on and learn a couple other things about random variables. We now know how to deal with functions of random variables. Related to this, but on face, just something independent about computing averages of functions about computing averages of uniform distributions is the notion of the average value of a function. This might be something that you learned in Calc 1, but I just want to relate it to random variables for a moment. So if we have a function f of x on an interval from a to b, then the average of that function is given by this formula all the way at the bottom of the definition. The average of the function is the 1 over the length of the interval times the area under the graph, or the signed area under the graph, the integral from a to b of f of x dx. We can interpret this as follows. If you let f of x be the distribution function for a continuous random variable capital X on an interval from a to b and then 0 outside, then the expected value of f of x, where capital X is a uniform random variable, is equal to the average of this function. The reason is that the function f of capital X, if x is a uniform random variable on a to b, is precisely 1 over b minus a. So the uniform random variable has as its distribution function 1 over b minus a. And we've actually seen this a couple times in class and in the previous lecture. Since that density function, or the distribution function for uniform variable x, is a constant, we can factor it out of the integral and obtain this formula. This is the formula that you may have learned before for the average value of function, but now interpreted in terms of random variables. And here we are taking the function f of that uniform random variable. Some other ways to interpret familiar things from integral calculus. Well, the signed area under the graph of a function is the integral from a to b of f of x dx, as we know and love. Another way to interpret the average here is that, well, if we take the average, which is a number, to be the height of a rectangle, that's the region under a horizontal line graph, then the area, or rather the signed area under that graph, is the width times the height of that rectangle. Well, the width of the rectangle is the length of the interval b minus a again. The height of the rectangle is the average value of the function, which we have a formula for. And that's just the signed area of that function, a to b f of x, the integral from a to b of f of x dx. You can see these things cancel out. But geometrically, graphically, how we interpret this is if we have a function and we can compute its average value, then the average value is the height of a rectangle having the same area as our function has from a to b. And here's a graph that explains this. The gold shaded region is the area under the graph of f of x from 1 to 9. And that area is some number. And there's some rectangle that has the same area and the same base width from 1 to 9. The height of that rectangle is actually given by this average value. So it was explained algebraically on the previous slide. Here's a graphical interpretation. Here's a problem that I'm not going to work out with you, but I encourage you to work out for yourself as an exercise. You can pause the video now or do this one at the end. Compute the average value of the following function from x equals 1 to x equals 3. Again, the formula for an average value of a function is 1 over the length of the interval times the signed area, or the definite integral of this function on that interval. The last thing that we're going to talk about in chapter 2, and the last thing we'll talk about probability for a while, is the notion of variance, which is related to standard deviation. The variance of a random variable x is, by one definition, the expected value, not of x, but of the new random variable, the function of a random variable, x minus its expected value quantity squared. We could call this thing in parentheses, this whole expression with the square, capital Y, a new random variable, since it is a function of capital X. And that makes it easier to see this as the expected value of this new random variable. If x is a continuous random variable and we know its density function f sub x, then the variance is given by this integral. This is the expected value formula, using the theorem that we learned earlier in this lecture, the integral from negative infinity to infinity of this new variable x minus its expected value quantity squared times fx of x dx. This is a definite integral. It's an improper integral, but it has, assuming it converges, it has a real number value. And that real number value is the variance. If we take the square root of that variance, then we get what's called the standard deviation of the random variable x. Standard deviation is usually written sigma. Variance is sometimes written sigma squared, but just like we write expected value as e bracket x, I'm going to write the variance as var bracket x, and I'll write this on the slide in one moment. So if the expected value, just to give a bit of visual interpretation to what variance is, if the expected value of this quantity x minus the expected value squared is larger, so the expected value of the new variable is larger, then what that means in terms of the spread of data in our probability space is that the random variable is more likely to take values farther from the expected value of capital X. So there are two graphs of probability density functions here. On the left, the values, or rather the outcomes of the random variable are symmetrically distributed around the mean or the expected value in the middle. But also they're sort of distributed in a way that most of the area, most of the probability occurs in the center of the distribution. So this is a one-humped distribution. On the other hand, and this has smaller variance than the other situation. On the other hand, if we have two humps or more of the data is clustered further from the mean, then we expect this to correspond to a larger variance or a larger expected value of this new variable. Here's an example. So we will practice with one uniform random variable together today. Let's compute the variance of a uniform random variable on the interval from 0 to 8. So I'm going to do this in a few pieces. So the first step is to write down the variance formula. And here you'll see I just mentioned, I'm going to write var bracket x to denote the variance. This is also sigma squared, and then sigma is the standard deviation, but I think this notation is a little better for now. So by definition, this is the following integral expression, and there are two pieces of information we need. We need the expected value of the original variable x, and we need the distribution function for x. I'm going to start with the distribution function. Remember from the previous lecture video that the distribution function for a uniform random variable is always given by 1 over b minus a. B minus a here is the length of the interval, so it's 1 over 8. And it's 0 outside of the interval. So just to remind you, this is what the whole function looks like. That's for a uniform distribution. The expected value of a uniform distribution, we can compute using an integral formula. But if you remember from one of the classwork activities, the expected value of a uniform distribution is actually the median, which is also the midway point in this case. So if the interval is 0 to 8, the expected value is 4 for uniform distribution. I believe we also computed this using an integral in the previous video. So with this information assembled, we can now compute the variance of this uniform random variable by integrating the whole stuff up above. I'm going to immediately convert this into an integral from 0 to 8, since the distribution function is 0 outside of that interval. So here we'll have x minus the expected value of 4 quantity squared times the distribution function, which is 1/8. And now this is a definite integral that you can go ahead and solve. So let me do this quickly for us. I'll pull out a 1/8 to handle this polynomial. We could probably do a u substitution and change the variable around, but I'm just going to distribute, FOIL this thing out, and I'll get 8x plus 16. And now just do the power rule to integrate. We'll have a 1/8 Here is the antiderivative we're looking for. Integrate from 0 to 8, or evaluate from 0 to 8. I'm going to keep a 1/8 all the way up front still. Notice that when I plug in 0, everything goes to 0. So I'm just going to have a single set of plugging in 8. I'm not going to compute the powers of 8 just yet because I have one out front to cancel. So here I have 4 times 8 squared and 16 times 8. And then the rest is 0. So let's distribute the 1/8. This will give us 8 squared, or 64 over 3. 8 cancels with one of the 8s. 4 times 8 is, let's see, 32. And 16 cancels with, or 8 cancels with one of the 8s. So we just get 16. So 64 minus 16, 64 thirds minus 16. If we get a common denominator, that's going to give us, I believe it'll be 16 thirds. So this is the variance of the continuous random variable x, that uniform random variable x on the interval from 0 to 8. From here, you can also practice by computing the standard deviation, which is the square root of the variance. And you can compute other things like probabilities under this distribution, although it's a uniform distribution and it's not so interesting. What does this really mean? It means that some percentage of the data strays from the mean, and if we move 16 thirds units away from the mean of 4, the expected value in the center of the distribution, then a good chunk of the data will stay within that interval to the left and right of 4. We're not going to go into much more detail about how much of the data stays within some number of standard deviations, but you can think of standard deviations as giving you units of movement away from the mean, and we can somehow quantify probabilities using that as well. All right, there's just a couple more things to wrap up. A couple takeaways from this, by the way. When we need to solve for variance, we first need to know the expected value. So we might have to compute this integral to find the expected value of our original variable. One thing that we saw graphically, but you can also deduce from the formula for variance, is that variance gets larger when the area under the graph is spread farther to both sides away from the mean. The reason that that's true algebraically is this expression x minus e bracket x squared, x minus the mean squared, gets larger, and therefore the entire function that we're integrating gets larger as x values stray from the mean. So if the dx, as our for our dx integral, if the x values along the axis we're computing have a higher probability further from the mean, then it'll be reflected in our formula for variance. Here's some summary questions, and I'll close with some exercises for you to work on. First, what kind of object is a function of a random variable? And given a function of a random variable, how do we compute its expected value? If someone mentions the average value of a function, what do you assume? How do you think about the average value of a function? And I'll add to that, knowing what you know now after this lecture, what's a new way of thinking about the average value of a function? Finally, how do we find variance? And how does variance relate to your expected value? And in particular, variance is the expected value of some random variable. What is that random variable? All right, that's it. There are no extra problems today, but we'll have some to work on in classwork. So thank you for tuning in, and I'll see you next time.